Hello, welcome to the video lecture series on Chapter 6.4 in the Lock 5 textbook. We're going to be looking at inferences for a difference in means in this chapter. All right, so here's our basic setup, and kind of the outline's the same as the rest of the sections in Chapter 6. We're going to look at the standard error and distribution for difference of means, then look at the central limit theorem for sample means. We're oftentimes going to use that t-distribution for difference of mean and when and how to use the t-distribution. Calculate confidence intervals for difference of means with interpretations, of course. And then we're going to do a hypothesis test for a difference in means. All right, let's start with the standard error formula. Standard error formula for the difference of two sample means, x bar 1 minus x bar 2, is given by this equation. Notice if you get rid of one of these standard deviations, you would end up back with the standard deviation over the square root of the sample size. But here, since we have two possible standard deviations, and don't forget this sigma stands for population standard deviation, we're going to take the standard deviation of the first group squared over the sample size plus standard deviation of the second group squared over the sample size. And as always, notice the larger the sample sizes, then the smaller the standard error becomes, because we'll be dividing by larger numbers. All right, the central limit theorem for the difference of two means is if n1 and n2 are sufficiently large, we're going to talk about this in a second, the difference of two sample means we could assume is normal. The center will be the difference of the two population means, and the standard error, or the standard deviation of the normal distribution, will be that standard error formula that we had on the last slide. And for our class, we're going to assume a normal distribution is a good approximation as long as both sample sizes are 30 or larger. Again, this, as I said before in class and other videos, these numbers aren't completely fixed. In previous stats textbooks I've seen anywhere between 25 and 40 for sample size. So this is not an exact number, but just to streamline things for our class, we're going to say as long as we have a sample size of at least 30, we could use the normal distribution. All right, let's look at math SATs by gender. So we're going to look at math SAT score. So that is a quantitative variable. But then we're going to break it down into gender, males versus females. So we have two categorical variables. So the math SAT score for males is 534, and get a standard deviation of 118. The average math SAT score for females is 500 with a standard deviation of 112. So suppose we were to take random samples of 50 males and 50 females. We want to find the distribution for the difference of means between these two sample groups. Well, here we would use that same formula. We're going to use the normal distribution. The first input, the center, is going to be the difference of the two population means. So that's going to be 34. 534 divided by, subtract 500. And the standard deviation of the normal distribution is going to be given by that standard error formula, where we take the square root of the standard deviation squared over the sample size plus the standard deviation squared over the sample size. And notice, if you enter this in your calculator, you need to add these two numbers first and then take the square root. And that's how you get 23.0078 would be the standard error, rounded to 23. Okay, you might be thinking this is nice for a situation like SAT score. Over a year, we actually have population information. Notice right here, these are all population variables, and we're given population information. These are the scores for the entire year. But oftentimes, we don't know the population standard deviations. So instead of using population standard deviations in the standard error formula, we're going to switch those to sample standard deviations. Remember, we use lowercase s to denote sample standard deviations. And if you remember, going back to section 6.2, we made the assumption that if we only know sample data, we do not know the population standard deviation. That is, we only know sample data. We're going to use that student t distribution. So when we replace this population standard deviations with the sample standard deviations, we're going to move from the normal, the z normal distribution, to a t distribution. And for our class, we're going to use the degrees of freedom as the smaller of the two sample sizes minus 1. Ooh, this is a pretty big typo. Okay. Okay, I'll make sure that's the slides are correct. I'm going to post these on Canvas. So the smaller of the two sample sizes minus 1. And just like before, if the population is approximately normal, or if the sample sizes are large. So we're going to look at, for using null hypothesis testing and confidence intervals, if we want to use the t distribution, we've got to make sure the sample sizes are both big enough, 30 or more, or we need to assume the population is normally distributed. And again, we're going to use the degrees of freedom to be the smaller of the sample size minus 1. Oh, wow. Okay, let me fix that typo again. Sheesh. Okay, smaller of each sample size minus 1. And our t test statistic is going to be the difference of the two sample means divided by the standard error formula, the square root of S1 squared over sample size plus S2 squared over sample size. All right, and then here's that standard error formula again. All right, so we've got all the information. Let's look at a couple of examples. For confidence interval, I need to put the formula down here first. The general formula for confidence interval, as always, is your statistic plus or minus z star times standard error. But if we do not know this population standard deviation, we're going to use the sample standard deviation and change that z star to a t star. So when we're looking at averages or means, we're going to take whatever the statistic is, x bar, or in this chapter, x bar 1 minus x bar 2, plus or minus the t star value, which we'll calculate it via stat key, times the standard error formula. And putting this all together for the difference of means, again, we need to assume the population is normally distributed or the sample sizes are big enough, at least 30. Then we have here the confidence interval formula, which I posted on your formulas handout. And as before, the t distribution, we're going to use degrees of freedom, the smaller of each sample size minus 1. All right, let's take an example. This is from, I think it was a 2011 study, 2011-12. There's a study of 210 first-year college students, and these were students that were living in a dorm or living on campus, randomly assigned roommates, and 78 students assigned to roommates who brought a video game system to college. So we're actually looking at does video games, having a video game system in your dorm room affect GPA? The average GPA after the first semester was 2.84, and the standard deviation was 0.669. For the 132 students, the rest of the sample of 210, 130 students were assigned to roommates who did not bring a video game system to college. Average GPA after the first semester was 3.105, so it's definitely a little higher, and a standard deviation of 0.625, so similar spreads. So the idea is, are these large enough difference to say that having a video game system lowers your GPA? So we're going to create a confidence interval. So how much does getting assigned a roommate who brings a video game system to college affect your first semester GPA? And again, these are people who are moving away from home, living in an on-campus dorm or apartment. Let's calculate a 90% confidence interval. All right, so I have the answer here on the slides, but I want to go through it a little bit more slowly. I only have one example for confidence interval and one example for hypothesis test on this video series. So I want to take some information. Let's make this a little bigger. Let's let n sub v denote the video game group. And out of that video game group, 78 is the sample size. We're going to use, excuse me, x bar subscript v. This will denote the average GPA of students whose roommate had a video game system. So that's 2.84. And S subscript V will be the standard deviation, 0.669. Let me double check with that. 0.669. All right, so that's my information for, put a note right here, this is my video game group. Notice we have two very distinct groups here, and no video game group. N sub, let's see, NV for no video game, that was 132, I believe. 132, we're assigned roommates who do not video game. Average GPA, that's overline subscript NV, that's 3.105, is the average, excuse me, GPA for those that did not have a video game. And then the standard deviation was 0.625. So S subscript NV, 0.625. All right, so then putting this together, we want a 90% confidence interval. So I want to make a note, since we only know sample data, in parentheses, we do not know population. We do not know any of the population standard deviations. We need to use T star. So I guess two reasons: we only know sample data, so use 2 star, and because both sample sizes are at least 30. All right, we got 78 and 132. So we can use the T star. So my degrees of freedom are DF is my degrees of freedom, and it's the smaller of the two sample sizes minus 1. So it's going to be 77 because it's the smaller of 77 minus 1 and 132 minus 1. So it's 77 or 131. We're going to pick 77 to be my degrees of freedom. All right, so then the formula says we're going to take the difference. We're going to take the difference of the two means. So I'm going to take the no video game minus the video game group. So that's plus or minus T star times standard error. So here's the formula you need to use. And we'll plug this in a second. The standard error formula is the square root of